Hello. Let's start this last section of the semester. It's going to be about linear algebra. More precisely, during these 4 classes that we have left, we are going to talk about more precisely about matrix algebra, linear algebra, but we're just going to keep the point of view of what's happening in Rn spaces and with matrices and vectors. Okay, things you already more or less know how to manipulate. And I guess that this first lesson is going to be just about reminding you of many things that you've already seen. Okay, but maybe with a slightly different point of view, because I'm going to follow the steps of Professor Gilbert Strang, a professor from the MIT, and he's presenting the linear algebra in, I would say, in a very different way than the one we use in France. But I think it's very valuable, and that's going to settle the right concepts so that we can go during the next semester, during semester 4, we can go to more general theory of linear algebra, which would be more like the French way of presenting things, where we are dealing with more abstract views of all these ideas. Okay, so let's have a look at what we can see. So Mr. Strang, Professor Strang, is so you can have a look at his page on the MIT website, or look for Gilbert Strang. I will give you the direct link for this if you like. He's now, I guess, something like 86 years old, but he's still teaching, and and the good thing is that he's been recording his classes for many years now, and so you've got the video lectures at the MIT classes that you can find online on the website of the MIT and also on YouTube, and these are some excellent references whenever you really want to get a nice overview of some topic. Okay, a very good overview of the topic. So we are going to have a look more precisely at that linear algebra 1806 class. All right, so I'm going to do something like a summary of these ideas, at least of the first part of the class, because these are things you've already seen last year, but maybe with a slightly different point of view. As you see, there are some books that he wrote. I wouldn't recommend them because, well, I think they are very good companions if you really follow his classes. But if you just want to learn from a book, I don't think these are the right books, except if you really know this professor very well and really know his way of teaching, because it's not like a classical books where you will find the good definitions and theorems. It's more like introducing things through examples, and it's very hard to follow, I think, when you read the book. It's very well to follow him. He is an absolutely fantastic pedagogical genius, but it's very hard to follow the written stuff he did. However, if you look at this class, so 1806, so let's open that in open class courseware, MIT Open Courseware, and you have all the video lectures, right? So we can click on video lectures, and then you can see you can have access to all the video lectures, which are about between 40 and 50 minutes long usually, and a lecture summary, which can give you the main points of the stuff. Okay, so I'm going to really follow these classes, except that I'm going to go a bit faster because, of course, you already know quite a few things about this. Okay, so let's begin today. Well, let's talk about, as his first class, the geometry of linear equation. Okay, so geometry of linear equation. Let's begin with some examples in 2 dimensions and in 3 dimensions. So, first example, let's begin with something that's not a matrix, but you know that you can put some matrices behind that. But let's have a look at a system of two linear equations. 2x minus y is equal to 0 and minus x plus 2y is equal to 3. Okay, this is a very usual system. It's linear in both its variables, x and y. What do I mean by that? Well, we will maybe see that a bit later, but this is just the kind of very typical equations where you don't have squares, you don't have any upper powers, you don't have x times y, you just have some constant times x plus some constant times y is equal to some value. What does it mean when you want to solve this linear equation? Well, you've got two ways to see that. You've got the row picture and you've got the column picture. Okay, so let's have a look at what it means to take the row picture of this equation. It means that I'm just going to look at each row separately. What is the first row giving you? Well, that's actually giving you a line equation. Line equation. Well, that's also one way to understand the name linear equation. Line equation, because this is really going to give you a line equation. And similar thing for the second equation, it's also a line equation, right? Okay, so what does it mean? Let's have a look at GeoGebra. If I draw these two lines, what does it mean? So I've represented that. Okay, so first line, given by this equation 2x minus y is equal to 0, you get that blue equation. Okay, and the second line, negative x plus 2y is equal to 3, so the red line. And so what does it mean to solve the system? It just means I want to find the intersection of those two lines, right? That is going to give me the pair of values x and y such that they satisfy both equations at the same time. Okay, so you clearly see that there's going to be some different possibilities. Either your two lines are intersecting, like this line, that like these two blue and red one. Either let's maybe take another one. Let's say 2x minus y is equal to, instead of 0, so it's the same left hand side as the first one, but instead of 0, let's take equals to well, let's say 3. Okay, so that's this new gray one. So let me just I don't want to see the. So now I've got those two equations, the blue represented by the blue line and the other one represented by the gray one. If I had given you this a system consisting of those two equations, well, you can geometrically see that you wouldn't have any solutions. Okay, why? Because those lines are just parallel lines and they are not going to intersect. Okay, so you would have something very similar as the previous case. So instead of that second row, if I had given to you, well, something very similar to the first row, maybe 2x minus y is equal to 3, which is the one that I gave you. 2x minus y is equal to 0. That would be another system. You see that here you have no solution. Okay, whereas in the first case, while those two lines intersected, you had one single solution. Okay, and again, then, well, I guess you see where I'm going to. What could I get if I gave you twice the same equation instead of, well, my two lines are just one onto the other. And so what does it mean? It means that I've got an infinity of solutions. It would just mean that the whole line would indeed be a solution. So instead of a 3, I give you 0 so that you get twice the same equation. Then you've got an infinity of solutions. Okay, so clearly here we have the row picture. You take each row, you interpret it as a line, and then a line in the plane, and you have those three solutions. Okay, now what about if I give you three equations? So I don't remember which choices I did, but let me just go back. So now if I've got three unknowns, okay, so X, Y, Z. So I'm looking for triplets of R3. So usually I'm going to write them in column. That's a better way, except when I want to gain some room. So, and I'm going to use line writing like X, Y, Z here. Okay. So if I give you three equations like AX plus BY plus CZ is equal to some constant value D, and I give you three of those equations. So let's say this would be a first one. That would be a second one. C2z is equal to D2, A3x plus B3y plus C3z is equal to D3. So if I give you three equations of the kind, this is again a linear system of equations, because I just have constant times my unknown plus next constant times my unknown and so on. All right, I don't have squares or higher powers. I don't have anything more than just multiplying they are unknown by a constant. Well, you already know that these are plane equations. Okay, so you see where I'm going to. This is going to give you the same kind of situations as the one we had earlier in the plane. So I did something about that. All right, so okay, so that's my GeoGebra representation. So that blue, light blue surface is the plane given by equation 2x plus 3y plus z is equal to 0. Now let me add one more plane equation. So minus 2y plus 3z is equal to 5. That's greenish one. So you know that unless they are parallel, two planes are going to intersect as a line. Okay, the common line to the first two planes, P1 and let's call them P1 and P2. And then if I add another plane, okay, represented by this reddish surface, right? It's going to intersect the first plane by a line, okay? That line at the intersection of the two plane. So that line belongs to the blue plane and the red plane. And then it's also going to intersect the green plane with a line that belongs to the green plane and the red plane, so that the intersection of all three is going to be the intersection of those two lines of intersection. Of those two lines that are given by the intersections of the planes 2 by 2. Okay, so you have one in that case here. You would have, okay, you see that that point that is at the intersection of those 3 points of those 3 planes. So you really have a unique one. If I had given you some parallel planes, you already see that that would be a problem. Okay, and if I had given you some planes that would actually be the same, you would maybe have an infinite number of solutions. Okay, so that was the row picture of those linear equations. Okay, let's now have a look at the column picture. Okay, so that was the row picture. Let's go to the column picture. Okay, so what do we mean by the column picture? Let me go back to my original two equations, system of two equations. 2x minus y is equal to 0 is equal to 0, and minus x plus 2y is equal to 3. So as you know, I can represent those x, y's as points in R2 or vectors in R2. So vectors is going to be our favorite nomination now. So, but this can be really expressed as x times the vector 2, -1 plus y times the vector -1, 2 equals to 0, 3. Okay, I've given you a vectorial expression of that system. Okay, in other words, what does that mean? I'm going to draw, well, let's draw my R2 plane. So that's x and y. And I've got my first vector. Let's call this vector, I don't know, let's call that A, and that vector, let's call this one B. So I is 2, -1, so it's going to land, you can represent it with an arrow around here. Okay, so that's my vector A. And my vector B is -1, 2. So something like that. Okay. So that's my vector B. And the idea is that can I do this kind of operation with my two vectors, so multiplying A by a value x and and adding B times the value y, so that I obtain the vector, this one, such that I obtain this one. Okay, so can I find x and y such that x times vector A plus y times vector B is equal to the vector C? As you already have some knowledge about this, you see that my vectors A and B are not collinear, okay? So that they can constitute a basis. You already know about this, but we will talk again about that, don't worry, of R2, so that I can describe any vector of any point in R2 by a linear combination of this. So I've got this term that is going to be quite important, which is called linear combination. Okay, so that will maybe our first definition. So in R2, we can begin with that. A linear combination of vectors in R2 in R2, a linear combination of A and B is going to be anything that can be written as a real lambda. Well, usually we use Greek letters for linear combinations, but it doesn't really matter. Lambda A plus mu B, that would be a linear combination, okay? And I've still written the arrows, but you know that I won't do that for a long time. Okay, so that would be a linear combination. Lambda is in R, mu is in R also. Okay, but I can do linear combinations of more than two vectors. So if I've got u, v, w, z vectors in R2 or even in Rn, okay, I can do as many, I can do anything looking like, well, let's call this alpha 1 u plus alpha 2 v plus alpha 3 w plus alpha 4 z. That would be a linear combination in Rn if alpha 1, alpha 2, alpha 3, alpha 4, my coefficients are real numbers. Okay, so the real, we even call them scalar. Okay, so scalar numbers, like we've already used that term. Scalar comes from scale. It's a way of scaling things, right? And maybe I can just still write the arrows to indicate that multiplying a vector by a scalar and adding vectors is something we want to do, okay? This is the basic of what is going to be called linear space or vector space. It's something where linear combination are okay. Okay, you take two vectors, you add them, you still have a vector, so you've got something called a vector space, right? You have one vector and you multiply the vector by a real number, by a scalar number. This is still a vector space. Okay, so for the moment, I've just given you the definition of linear combination, right? And so the column picture of my system was really about saying, well, if I look at my system as this vector equation, it's really, can I find a linear combination of my vector A and my vector B that gives me the vector C? Okay, and you would have something very similar for the 3-3 system, saying that if you've got a1x plus b1y plus c1z is equal to d1, etc. So same stuff with a2, a3. The column picture of this system would be, can I find x such that if I multiply it by vector a1, a2, a3, and then add maybe find y such that if I multiply it by b1, b2, b3 plus z, c1, c2, c3 is equal to d1, d2, d3. Can I find a linear combination of my three vectors? So let's call them again vector a, b, and well, this is the c, and that's going to be the d. Can I find a linear combination of a, b, and c? So x times a plus y times b plus z times c is equal to my vector d. Okay, so each of those belong to R3, but well, you can imagine that I'm going to go further. In R3, we can still represent things. So let's say you've got X, Y, and Z. You already know that if I've got, let's say that would be vector A, maybe I can write vector B like something like this, and vector C like this one. So you already know that if I've got three vectors that are not collinear in R3, I will be able to attend to reach any vector D, any point in my plane. I can find a linear combination of those three vectors that will work. But if I had given you vectors that would have been instead of those three nice direction, if instead of that I would have given you, let's say, let me erase that, and let's say a vector C that would be the opposite of vector A. You see that this way I would only have been able to describe anything that would be in the plane given by vector A and vector B, and so that if my D didn't belong to that plane, I would never be able to find such a linear combination. Okay, so that was an overview of, well, just the first idea of the thing we're going to do, except that we're not really going to work on systems, but directly on matrices, which I haven't written yet. But I hope that you know that, for instance, that second system can be written as, can rewrite it as a matrix A1, A2, A3. So I put in the columns my three vectors A, B, and C, B1, B2, B3, C1, C2, C3, times my vector X, Y, Z, well, my vector of unknowns. And what I really want to solve is this thing equals to D1, D2, and D3. Okay, so that would be, and well, of course, you remember that's that you can write this matrix equation row by row, and you find again the system that you had. Okay, all right, so let's end that first video, and then we will see that the matrix multiplication that we have here, we can also see it as a row picture and as a column picture, and that's going to be directly related to those two views of my systems that we had here. Thank you.